Hello, good morning everyone. I am Dr. G.M. Dharani, Department of Physics, Dr. Babasaheb Ambedkar, Marathwada University, Aurangabad, India. So due to this COVID, it is not possible to come students at the department and do some practicals and some theory classes offline. Okay, so for this I have made here this measurement of susceptibility of a materials. Okay, and that can be measured with the help of magnetic susceptibility balance MK1 instrument. This is a Sherwood scientific instrument, Cambridge, produced at Cambridge. Okay, first of all, what you have to do in this case, you have to switch on this button. Means you have to switch on power supply, and you have to keep this warm around 10 minutes. Here I have taken, we are kept for half an hour, no problem for this. Okay, then you have to adjust this zero here, means spirit level here. Okay, then there is a zero knob. With the zero knob we can adjust this zero here. If getting it is zero, then no problem. And here, even though if you are not getting in this case zero, that means that may be the error, you can say. If the error it is getting negative, then you have to add that error in the while taking the readings. And if it is error is positive, then that error is to be subtracted from the readings. Okay, so in this case we have given three capillary tube. One is for standard, that is for MnCl2 sample. Another two empty tube, empty capillary tube. Its diameter is also given here. Okay, now to measure this, to take the reading, what you have to do, first of all you have to take the empty weight. First of all you have to take empty weight of this capillary tube. Okay, taking this empty weight, you have to again put inside this hole. It will show some reading. Okay, it is showing some reading here. Okay, then you can say that is R0. You can see this is R0, no problem. Okay, then you have to fill this sample inside this. You can fill directly also like this, or we can take spatula and fill, and you have to just tap here. Just you have to tap here, so that the sample can be closely packed. Okay, after filling sample in this capillary tube, what you have to do, you have to fill the sample around 3 centimeter or 2/3 of this capacity, you can say. Okay, after filling that, you have to make it clean again. You have to make clean with the help of cotton, because no any particle can be go inside this. Okay, because it is very sensitive instrument. Okay, so by doing this, you have to insert here. It is showing some readings. Okay, it is showing some reading here. Okay, then this is reading R. Previously initially that was R0. Then we have formula to calculate the volume susceptibility. So here first of all you have to calculate the volume susceptibility, and that volume susceptibility we know that it is psi V equal to some constant into R minus R0 by area. Okay, to calculate the area, here you are given the radius of this, so you can measure the radius of this capillary, empty capillary tube also. This empty capillary tube, you can measure the radius with the help of traveling microscope also, no problem. Or it is now given for this. Okay, if it is unknown or another new one, then you can measure the radius for that also to calculate the area. Okay, so here this volume susceptibility equal to is formula as a C into some C into R minus R0. R is the reading of the sample and R0 is the initial reading. Okay, upon area. So using this formula you can calculate the volume susceptibility. Okay, so here where the C is the constant or it is produced at the time of production constant, that is C balance upon 10 raised to power 9, or you can use here this constant as a C equal to 1 into 10 raised to power minus 9. After calculating this, we can calculate the mass susceptibility, and that mass susceptibility equal to x m, as you can say psi m is just symbolized just like x, it is psi m equal to volume susceptibility upon density. Okay, and the density can be calculated by mass of the sample upon length into area. So you know the area, and you have to take the length as a this length, means measuring the length of this length of the sample. So it is around it is just you have to measure accurately. It is 2.4, sorry 3.4. That length is, it is 3.4 centimeter. Okay, so from this you can calculate density. That means density equal to mass of the sample. That means after taking out this, you have to weigh out its mass on this balance. Okay, digital balance, and from this we get mass of the sample. That means this mass and this initial mass of this empty capillary tube. We will get this mass of that sample upon length and into area. This gives the density. Getting this, we can calculate mass susceptibility, and from this we can get from this we can calculate the molar susceptibility, and that molar susceptibility equal to this mass susceptibility into molecular mass or molecular weight. Okay, then with the using this we can calculate the molar susceptibility. So here again we are given one standard sample, that is MnCl2. For MnCl2 as a standard sample, it is liquid. Here we just use pour inside this. Okay, it is showing some reading here. It is now 994. It is 994. Around the may 1-2 digit may vary. Okay, now taking this reading, and you have this empty sample also, empty capillary tube. Okay, again here you can calculate the volume susceptibility, mass susceptibility, and from that we can calculate molar susceptibility. Now calculating this, we calculate here, and that is getting here 7.2, means it's a mass susceptibility equal to, we are getting here 7.28 10 raised to power minus 2 in CGS system, and if you multiply this with a molecular weight, it is that was 1.97.7, and if you multiply this, then multiplying we get it is 1.44 into 10 raised to power minus 2 in CGS system. Okay, and while the is a literature value of this molar susceptibility of this MnCl2, it is 1.46 into 10 raised to power minus 2 in CGS system. That means both values are nearly matched. So this is for the standard sample. That's in this way, by using this method, we can calculate the molar susceptibility of any material, even liquid material as well as solid material. And again further we can extend this as a, we can calculate the number of unpaired electron per unit area in that sample. Okay, in this way we can calculate, or this balance can be used for this purpose. Okay, thank you, bye, thank you very much.